So we would like to reject this one.
We would like to challenge problem number 13.
We would like to reject this one.
We would like to challenge problem 11.
We will accept that.
这样子 OK 了吗？
他们记得，他们记得。
The reporter and the reviewer should write your name on the report.
Can I start right now? It is available to start early.
Okay, you can.
Yes. Good morning, honorable juries and fellow participants. I'm going to present our research on spring categories. I'm the reporter mentioned from Tina's cabinet. This is a problem statement. The spring categories. We have connected two identical linear springs symmetrically to a base in a V shape and applied an adjustable force to the mass. When this force is varied, the resource of motion of the mass depends on the history of change in the applied force under certain condition. Therefore, that comes from the three crucial questions. Question 1. Which model can explain the phenomenon? Question 2, what are the parameters? And question 3, what are the main causes of the energy decay? Now this is an overview of the constant. Now I'll go to the introduction part. This is a video of it. Please follow these 3 points. As you can see, this is the highest point that first ball have achieved. As time flows, this ball should be decreased of its highest points. So that is an unique motion that we call a damping. Now I have a roughly introduction of the parameter. First of all, n, which stands for the mass of the ball. L0 is each spring's nature length. Nature length, I define it as without any applied force to the string and its nature length. So K, which stands for kinetic constant of each spring. Next page. X, the horizontal separation of distance. That means from the middle of the ball to the wall, which is as known as a fixed point of this experiments. Next page. Y0, the equilibrium position of this ball. And F. Next page. F, the extra force that I applied on this ball. This is the experiment setup. Now from this arrow, you can see the wall, which is a fixed point, and I stabilize it pretty well, so there won't have any horizontal motions on this system. Second, the spring and the ball. This one. First, this is the spring weight scale, which I used to measure my force applied on this ball. And this is exploding resin, as known as AB glue. I applied it into the ball to increase the mass of the ball instead of choosing another kind of material. The theoretic model. First of all, the extra force has been applied to the ball, and the string will have a horizontal force that will cause it on the ball. Well, the extra force is there. Then there will be a opposite velocity will be caused to the ball. As we can know, the damping motion is F damping is equals to CV, which is have a positive coefficient, positive correlation to V, and the extra force will have a positive correlation to the acceleration of this damping. And the damping force, I have a prediction of this. A faster object has a higher damping force. This page. This is a theoretic model, which is a quantitative theory. Now, I do some numerical simulation which use Python as a assistance. So, this page. Now, I have discussed about the spring force and the extra force, which is this formula. Please take a look at it. The damping force that I talked previously. And the total force will be calculated with this formula, which is the damping force and the spring force. But as we have known, the damping force and the spring force will be in the opposite way, so this is a minus. And the acceleration can be calculated with this formula. Now, I've done some numerical, I've done some equation of this motion. As we have known, this is a very typical, very classic damping motion. And you can get the characteristics group, which is this. As we have known, when C squared and H have 3 kinds of conditions, please look at the whiteboard, please. If C squared is bigger than 8kf, from this chart, we can know if the ball has a motion of this. This is while C is bigger than 8kf, which is known as overdamping. Well, C equals to 8kf is as known as critical damping, which will have a chart like this, to 0, limited to approximate to 0. Well, C is lesser than 8km. It will cause a motion called underdamping, which looks like this. This is therefore, well, C is under 8km. That is what we are going to discuss in this experiments. And here, no, upper. But as we have known, this formula is only suitable for a single spring system of damping. Therefore, with forward with forward formula, we can rephrase this formula to a two-spring system. As you can see, this is the period of this damping motion. Next page, please. Yes. And as we have known, I want to make it closer to a reality situation. Therefore, every system correction is a must to this experiment. And as you can see, the low air is known as 1.23 kilogram per cubic meter, and the V squared times CD. Well, you can see CD is at here, but it is above, so it is known as a sphere. So the drag coefficient is 0.47, which is known as CD. And the area is calculated by. But the ball I use is a ping pong ball, so I will discuss it about later. Now it's the experiment part. From the chart, we can see. First of all, I've done a different K, which is known as the elastic constant. The elastic constant in this first experiment stands for 0.07 Newton per meter. As you can see, the red dot stands for the experimental data. And the green dots, the green line, this green line, the thinner one, which stands for the simulated data that I have done with Python code. So as you can see, they fit each other very, very closely. Therefore, we can discuss that the accuracy of this formula is pretty nice. First, please take a look at the period of this data. The period is 4.923 seconds, and the decay rate, which is known as the thicker green line like this. We can know that y is equals to this formula. Next page. And while K is equals to 5.81 Newton per meter, as you can see, the period rapidly decreases. Therefore, I have a prediction of different K. Therefore, higher K cause the period to decrease, and the decay rate is go up. Let's look at this number. It also have a highly increase. Therefore, I think that a higher K causes the decay rate to increase. You can also see from the chart. Next page. Now we will discuss about different extra force. First of all, the two-spring is ideal spring, mostly ideal spring, and this is also known as experiment data and the simulated data. I have applied a force of 9.8 Newton to the ball, and this is the period and the decay rate. Yes, and the second extra force I have applied on this ball is 14.2 Newton, and the period is this, and the decay rate is go. As you can see, the period didn't change a lot. Also the decay rate. Let's take a look at these data. Now we'll go to the conclusion. First of all, the factors those influence your period. I think extra force does not influence your period of this damping function. But the higher the K is, lower the period is. Second, a factor that influences decay rates. First of all, as I have said previously, extra force does not influence your decay rates to this damping function, but a higher K also creates a higher decay rate to the whole motion. That's it for my presentation.
Okay, the question from the opponent.
Okay, so turn to page 20.
Yes.
Okay, so is what function did you try to fit the terminal data?
As I have said from the quantitative, this one. But this one is a single screen system. Therefore, I have do some rephrase of it with the forward formula.
So this only considers one screen.
This is only considering one screen.
Okay, and page 22. Is the force constant?
Yes.
Okay, then page 5.
Yes, sir.
Okay, I go back to the you considered the horizontal movement of the ball?
Oh yes, because I think I can do that in a discussion because that will be a long answer. Is that
Okay. And another question: have you considered the gravity of the ball?
yes, of course.
And then where is it in the equations?
In the equations?
I didn't see that.
Next page. The end.
No, I mean the gravitational force of the.
The gravitational force. Oh, in this case, we didn't.
No, not the gravitational. Yes. Go on. That is the mass, not the gravitational force. Where is the gravitational force?
As in this experience, gravitational force is not. It won't influence the whole experience.
So in this case, you have considered damping as C, right?
Okay, answer.
Thank you.
Okay, the opponent takes the floor.
Okay, so greetings dear debaters and jurors, and I am the opponent from the Lagrange team, and today I'm going to be opposing on problem number 11, the spring hysteresis. Okay, so this will be my quote. Okay, so first let's take a problem recap. The problem statement has explicitly mentioned in its name the hysteresis, and it mentioned the very force as well. So I suspect that they have completely investigated the wrong phenomenon and put a wrong focus on the damping, which means that their report is inconsistent with the problem statement. So they have no consideration of hysteresis, which is the equilibriums of the different force and the placement, and which will be affected during the movement of the phenomenon. So this is the general pros and cons. It is a well-organized report, although it has nothing to do with the problem statement. And it has a quantified theory and numerical solution. And the cons is the no intuitive explanation and no explanation on the hysteresis, which is pretty essential to the problem statement. And the x-axis movement is not discussed, nor is deviation analyzed. And they have a lack of experiment precisely with the geometric configuration of the spring. And the velocity is also not considered, and the very force has not been measured. And this is the report overview. So first, they have defined the parameters and have a clear observation video. However, I think their setup is not robust, and they have no consideration of horizontal motion. Step 2, they have remodeling, which they use damping to model the movement of the spring. So I think it's pretty good that they use a numerical solution. However, they should not use a blackboard to explain the overdamping, which means that their report is incomplete. And they have no consideration of gravitational force and only consideration of the mass, which I think is a big problem. And step 3, they do experiments with the ping pong ball, which is attached to the springs. And however, when they fit the experimental results, they only fit with a single spring model, which they have not explained why this is suitable in this condition. They have also calculated the decay rate and indicated that the decay rate is not influenced by other factors. However, this has nothing to do with the hysteresis phenomenon. And then the missed points will be the very force, which is mentioned in the problem statement, and the hysteresis, and the use of a single spring model. So this will be the discussing points, which I will ask the reporter about the force and the motion, and ask about why they put such an emphasis on the damping. And the experiment and other experiments and setup is that the experiments only calculated the damping coefficient. And I would like to ask its relation with the hysteresis phenomenon. And the data analysis, I would like to ask the reporter about its deviation from the theory, as I can see from their graphs. And I would like them to explain what will happen to their graphs if they actually done the very force and the hysteresis phenomenon. And that will be my Okay, so can you turn to the observation video? The observation video. Okay, so have you tracked the motion of the?
Yes, I do track the points.
Do you have any graphs for that?
Yes, exactly. The graph part is which one is. Oh, the red dot part is the experiment data.
Oh, so what exactly, can you clarify on what experiment is this?
Oh, this is the movement on y-axis.
Have you considered the x-axis movement?
Oh, I think I mistyped it. But this is also just considering the y-axis, because the x-axis will be something like another damping motions that will do in a classic way. It will do something like this.
So you fit with a single spring model?
No, as mentioned, I think you misunderstood that a single string model should be like this.
What is force? And so what is the fitting right?
This fitting is, I rephrase it. This one is a simple one, right?
Yes.
So I rephrase it into a double, two spring systems.
I thought you used a numerical solution.
Yes, I do use a numerical solution, but this formula is focusing on the single string system. So I replace
what is the correlation with the phenomenon?
with The experiment is focusing on damping motion on the y-axis.
And what is the relation with the damping motion with the phenomenon of the hysteresis?
Hysteresis.
Well, since I can tell you that this, when you have a force like this, then like you may write down your equations of the force and the displacement of the y.
Pardon?
If you have like a spring right here,
Yes.
right? Then what is the equation of the force right here in your theory?
In my theory, that will be equal to an oscillation. It will be y times 1 minus L0.
Yes. So if you like draw a graph in here, with the y to the f,
Yes.
and then the graph will probably look like something like this. Right?
Oh, I think it means. I think it means it will be the same thing divided by this. Oh, I mean, like this.
Well, no, this depends on the value of the x and the L0.
Yeah, it is.
So sometimes it will like look like this, and sometimes it will look like this.
Yes.
So have you discussed this?
It means that hysteresis.
It's meaning that in a like you calculate the motion, right?
Yes.
And you have the different y, right?
Yes.
And you calculate the y. So in your graph, you have displayed the y to the t.
Yes.
Okay, so at different y's, there will like be different varied motion.
Yes, exactly.
And because the varied motion is caused by the different forces.
Yes, exactly.
Yes. So have you considered this?
I think this the chart can explain this because if your motion force is highly connected to your position, right?
Yes.
I think I will do it exactly right. Yes. So you can consider the damping motion to hysteresis.
But this is not an idea. And so what you're seeing here, this is the damping motion, right?
Yeah, exactly.
Yes, but damping motion is I know that damping motion is related to the
Yes.
to this formula.
Yes.
Yes, but here the force is varied since this is a nonlinear equation, and you should have calculated the force on the different y.
Force on different y.
Yes. And this, okay, so here, as you can see from the theory, right? So you have drawn a graph like this. But
Yes.
however, if you change the L0 and the x, so that the L0 will like get bigger than the x, then the graph will look something like this.
Exactly.
Yes, so this is the phenomenon that you are supposed to be focusing on, which is the hysteresis motion. So in the graphs, we cannot see the hysteresis because you only, in your experiments, you have only considered this case. However, you miss other cases of the phenomenon.
This phenomenon, I think, this will be L0, which is smaller than x, isn't it?
Yes.
So, while the damping motion goes to, when it is approximately, when this damping motion is approximately to 0, right? So, the motion of it will be something like this, while the y0 is smaller than x.
Okay, so where is the hysteresis in your philosophy?
I think I didn't show
In front.
You mean
The hysteresis of the motion.
this motion. So I think it's something like this. Oh, this one, this is the first case. This is the first case, right?
Yes.
We have none. And if we discuss on the axis, so it will be something like this. Well, the spring will have an extra force that is caused by both. So the L0 will be lesser than your x.
For considerations, it should look like something like this.
Yes, exactly.
And it will have like two stable equilibrium points up here and one unstable equilibrium right here.
Yes.
This point, and this one.
Yes.
Yes. So in your experiment, have you considered this?
In my experiment, no, my experiment is focusing on damping motion, the motion.
Okay, so what is the damping motion's relation to the hysteresis phenomenon?
I believe that the motion is highly connected with this phenomenon because the heat.
Okay, so your experiments, you have constant force.
Pardon?
Can I see your experimental results? Yes, next page. Okay, this. So in this experiment, you have an extra force. Yes. However, the problem statement has mentioned the varying force.
Very force.
So what will happen if we have given a varying force to this spring?
It means that that force is while the spring is in a nature position, and the force is applied here.
Yes, and the force will be a function of time.
Yes, so it will. In my experiments, that the force is applied. It will be this case. The mean will be something
but if the force is changing over time, then what will happen?
Means what will happen in my opinion.
Yes, in your opinion.
It means at the y-axis or the x-axis.
Of course, if your definition, because you have y-axis and t. So if you're only defining a horizontal motion, then what will happen?
If this is a horizontal motion, I think.
Oh, no, I want the BT graphs.
BT.
Yes, BT graphs.
So it will be something like this.
Why?
Why?
Yes, because if the force is very well, I think this will depend on the varying force.
Yeah, it will depend on the very
So in this phenomenon right here, you have, let's say you have this given the spring constant force.
Yes.
Right? What is the method? I mean, you give it a weight or?
I use the spring step to apply the same force. I've calculated. It's not calculated. I measure it. The force.
So the force is constant.
The force is constant. I've done 2 extra forces.
Okay, so this is a YT graph. Do you have a velocity? Because I think for the motion, it is more important for.
I did not put it on this, but I believe you will do something like that.
Okay, so back to your observation video.
Yes.
Okay, so I think in the observation video, you use your hand, right?
Oh, because this is just I'm not going to show you a phenomenon, but in the experiment setup.
Oh, no. I mean, if you use your hand and use a Pascal or something like that, and you generate a different varying force, then you can actually observe the phenomenon, which the problem statement is mentioning about.
Oh, I got your points.
Okay, so and in this observation video, we can see that there is it's not in the 2D plane, and if you have conducted a better experiment or methods like using something like this, then you can get it into a 2D plane. Okay, so to summarize the discussion, the reporter has no experience on the phenomenon which the problem statement is mentioning about, which is the hysteresis. Okay, so the hysteresis right here will differ from the conditions of the original natural length and the distance between the 2 nails, and they have no experiments on this. And they only have calculations of the damping and its set factors. And also we have discussed about how they can improve their experiments by using Pascal to really give the ball a varying force and to observe the motion. And it can improve its experimental methods by using some piston like this to configure it to a 2D plane with only vertical motion and rule out the horizontal motion. And that will be my summarization.
Hello, I'm the reviewer of this problem. So I want to ask the reporter, what is the definition of the hysteresis and also you?
I believe it is hysteresis.
What is the definition, do you think?
I think it's a decretion.
Okay, so what do you think?
I think the hysteresis is the nonlinear equations caused by the V-shaped spring.
So I know. So do you think that the hysteresis is highly related to the extra force change, so that it is a function of the time? So what do you think?
Can you repeat the question?
The hysteresis is highly related to the change of the force,
The very
extra force. Yeah.
I believe it is.
Also, what do you say?
Well, I think the hysteresis is related to the extra force change, as you mentioned, but it's also related to the position and the velocity.
Okay, I see. So, next question. What is the cause of the damping?
The cause of the damping, it might be an energy
So
transformation.
the spring or the air drag force?
The spring and the air drag force are.
Okay,
both.
so both you think also what do you
Well, I
think?
think the damping is caused by energy dissipation in the
So
system.
dissipation, what is the source of the dissipation?
Well, might be caused by friction and
Friction, spring friction?
both the spring and the air resistance.
Okay, so how do you think? You mentioned that the air drag force is proportional to v squared, but your model is proportional to v linear. So your model there's some inconsistency. So what do you think about this?
I believe that the damping motion is a slow. Relatively, it is a slow movement. Therefore, I decided. I have to do some experiments on it to find out that.
Okay. So how do you think? There's v squared and v.
For a slow speed, I think that is proportional to the v.
Okay. For you question, force extra is your weight, right? The weight, the gravitational force.
Force extra?
Yeah, force extra.
No, it's the applied force by pulling the ball.
Okay. Okay. So question for you. There are more than one equilibrium point. Do you think?
Yes, it
right?
is.
How do you think?
There are 3 equilibrium points, with 2 stable and 1 unstable.
Yeah. Okay. So the next question, the damping force should be counted in the extra force. Do you think? Damping force should be counted in the extra force.
OK，谈一下。
Okay. Thank you. Hello, I'm the reviewer of this problem. So I'm the reviewer, and I want to see the pros of the reporter. And their observation is damping, is focusing, and they define a lot of parameters, their cons, but their pros is this, and con is didn't show the decay precisely. And the theory have a quantified explanation and numerical simulation consider air drag force, which is their pros, but the cons is no damping situation in the sides and no discuss of hysteresis, which is a very important point of this question, and they only consider about one spring. Their theory only consider about their one spring. And their experiment pros is they show the data quantified and find relation on decay rate and period and qualitative conclusion. But their cons is the parameter too less, and they didn't give a well explanation, and they didn't show the hysteresis, and they don't change. They change mg. Mg is they change the gravitational force and the mass at the same time. There are no controlled variables. And the next one cons is they didn't change the trajectory and the force, and which is a very important point for hysteresis. Okay, so review of propositions. The presentation is point out their midpoint, which is hysteresis, but their cons is that they show their own results of those graphs. And their show question mentioned that their fitting method is like to fit the one spring model, and the second one is simulation condition. And the pros is they're short and clear, but the cons is that they didn't catch the main point of the problem statement, which is the hysteresis. Okay, so there's a key discussion of the opponent and reporter. Say the first one is opponent. They think no data about the theory of one spring, and the reporter they show their data and they showed a man from the one spring to the two springs, and we think both didn't understand the question here. Okay, so the theory discussion, the opponents say that they think should consider a man from the trajectory of the mass, but reporter say they can explain their data, but we think that is very important because it is a problem statement, the hysteresis. Okay, so the experiment discussion, the opponent says they think the hysteresis motion is much important because the data couldn't explain well, and reporters say they didn't consider about the hysteresis. Okay, so we think we agree of the opponent. Okay, so experiment discussion, the opponent thinks the force should be function of time, but reporters say this is a constant, and reviewer we think the force should be the function of time because it is the hysteresis source. And the experiment. Okay, so our question is the first one is the definition is hysteresis. Opponents say the nonlinear constriction. Reporter also says nonlinear constriction. And the reviewer, I say that the motion is related to the change of extra force. Opponents say yes. Reporter say no. And I ask about the damping causing. Opponent and reporter say false air draft and friction. And thank you.
I will do I will do a conclusion remark of the 11th problem, spirit hazards. First remark point is the formula rephrase. I think I have said that the formula have been rephrased into a two-spring model. It's not a single-spring model. And the damping part, I think that, well, the hysteresis will cause the damping to happen. Therefore, I've designed my experience to be a damping motion. And that's it for the remark. And about the reviewers, I think you have understood about something that in the previous discussion that I didn't mention any single spring system in the paragraph, in speech. That's it.
So it's okay. So any question from the jury's presentation?
Question for the reporter. You replace the two screen with one screen. What change you
Pardon?
You model the two screen with one screen formula.
No, I replaced the single screen
So
model
what difference between two screen and one screen? Any change? How do you change?
I have been changed.
Yeah.
Most of the parameters will have another way to show it.
For the reviewer, what is the research, key feature of his research? What is the key feature of his research?
I think it is the history of the force the history of force should affect the trajectory of the mass.
For the opponent, what you consider is the research?
The hysteresis is caused by because I think the motion should be a function of the displacement and the extra force and the time. So the hysteresis is caused by a non-linear equation. So it will have different equilibrium points depending on the conditions of the x and the natural length and the very force and the movement.
I noticed that your observed data have a consistent bias towards the positive direction along in the y direction. Can you show the data? Any data? Did you notice that? All your data have a consistent bias towards the positive displacement in y direction.
Yes.
Yes, and can you explain why?
You mean this part?
Yeah.
Oh, because most of this is, I think it's because of well, I use tracker for it. Therefore, there will maybe have some error here. There will have some experience error.
But it's not random error, it's a bias to the positive direction. And I want to ask you the other opponent and the reviewer.
I think that the fit constant might be wrong. So if he change the constant of the fitting function, it might fit the experimental data well.
Well, I think that they might have misconsidered the gravity right here because it has a bias that is consistent, which means that maybe the weight of the ping pong ball has not been consistent.
Any other question?
So, what opponent talked about the two-dimensional motion. If that case, what kind of condition you need to consider? I would like to see hear all the new opinion on the two-dimensional.
So if it is like, so this actually might be a three-dimensional motion, but if you're only considering the three-dimensional motion of the plane, then it will like be the x, there will be the x and y, and the y will exhibit the hysteresis motion, and the x will have like a damping motion that could be as error, but if it has better experimental methods, this can be different.
I think we can restrict the motion of the mass by like a paper or like just a paper, something like restrict the mass to the 2D motion or like that. But if there's no those restriction, we should consider the 3D motion.
At the previous speech, that the reviewer the opponent have showed that that things that is with a rod, I believe that it can control the ball in the 2D dimension.
I have a question for reporter and poll reviewer. The reporter have a system use two screen, Do you think his spring could observe the hysteresis by using their spring? Could you show your system picture again? Yeah. Opponent, do you think if you use this kind of spring, you can observe the hysteresis phenomenon? Yes or no?
It depends on the spring's natural length relation to the x. And I think here it is not.
Okay. Review.
If the spring is compressible, I think it's right. Yes, but I don't.
So, is this spring compressible?
I don't know. It's this experimental setup.
Okay. Okay. Thank you.
Can I say some point about the previous question?
Yeah.
I think if the spring is compressible, then we can observe multiple equilibrium points.
Yeah, I know
And-
your point. Yeah.
And the multiple equilibrium points could cause the hysteresis phenomenon.
Yeah, but in this case, they use uncompressible springs. Right.
Okay, score for the reporter. 5, 4, 5, 5, 4. And the score for the opponent. 7, 8, 8, 8, and 8. And for the reviewer, 6, 8, 7, 7, 8. Okay. And this competition was closed. Okay, thank you.